time for welcoming again to the stage Marco Müller, or Dr. Marco Müller, founder and managing director of Bionics, board member of Open Charge Alliance and Linux Foundation Energy, and chairman of Project EVerest.
Thank you, Michael. Thank you everyone for being here. I would love to give you, as promised for today, another tech talk. So let's dive into how DC charging actually works. I mean, everyone here has experience in, I think, a lot of operating charging station, but what are the under the hood principles? And before we go into the hardware, I would love to walk through the protocol and the different steps. So, communication overview. Where does everything start? Normally you have two signals between the charging station and the vehicle. There's one PWM signal, so a rectangular signal between plus and minus 12 volts with 1 kilohertz, and on top of that there's an Ethernet communication link, also sometimes called home plug green-fi. Especially this home plug green-fi was kind of a later on addition, because they just had not enough bandwidth on signals left to build proper DC charging. So how does it work? Let's walk through the states. If you arrive at the charging station, sure, you have to plug in your car. What happens next? The charging station enables this PWM signal with 5% duty cycles, so only very short spikes between minus 12 and plus 9 volt, signaling I want to do high-level communication. Yeah, there is this PWM signal, but actually we will ignore it for the most of the session. We want to do this high-level communication. And basically this is the first signal letting the car know. So the car next goes into try to establish a network connection. The problem is with this green-fi power modem is you have a shared medium. So you're communicating on that wire, and the car can hear you, and the charging station can hear you, and if you're lucky, all neighbor cars, neighbor charging station as well. It feels like a point-to-point connection, but since this is the same stuff you're using at home to bridging your network through the power plugs, it really, really well travels through power lines, so also where you don't want to have it. So how do you identify which one is the car you're actually connecting to? So you have two people at least speaking on that wire, but actually more. So how do they find who are the ones who are now plugged together? So the idea is the car gives a broadcast like, I'm here, who else is here? And then all charging station reply, yes, I'm here, can you hear me? And within that response, they're giving a signal strength. Oh, I was able to listen to the car, I listened in that volume, and then the car can decide, probably the most loudest charging station is the one I'm connected to. If you're coming from IT security background, you would really realize, what if the charging station lies about that signal strength? If someone just tells, oh, I can understand you pretty well, and actually you're on the other side of the parking ground. So you can easily hijack communication here in that phase, and can play easily man-in-the-middle attacks. No one talks about this in our industry, but there's no security built in this layer. Everyone responds with signal-to-noise ratio, and if then the car and the charging station are not sure if you could connected to the right one, they can try to toggle on this 12-volt plus-minus line a bit between different states and try to find out if I'm really connected to the right one. This is not about security. You also could interrupt this because you have to signal a number between 1 and 3, so you can probably guess which number this is with a really high chance of winning. So after all of this is established, they know who to connect to. They establishing a logical network. So and from now on, if this is connected, there is secure end-to-end communication. Except there might be someone else in the middle and interrupting it. So if the network is now up and running, the EV broadcast within that network, who's there? What kind of encryption should we do? Then the EVSE, so the charging station replies with IP address, port numbers, and what kind of encryption it should use. So then they slightly start to go into next step, what protocol should we use? Yes, we agreed on a TCP connection, but what language should we talk about that link? So they realize it's a stack of protocols on top of each other. So they can choose between typically DIN spec 70.121 or IC5011-8-2 or DIN Tesla or IC5011-8-20. And to be honest, under the hood, many of those protocols have actually a lot of sub-dialects they can't distinguish. So they can only in a high level distinguish which protocol this actually is, and everything else is then, let's say, guesswork later on. Like, especially for DIN spec 70.121, everyone is doing it slightly different, and you have to be flexible while speaking that protocol. Okay, after that is selected, initiate of charging session. The EV sends its ID, so for example, its MAC address, especially for Volkswagen Group cars, this is a random number, so it's every time a new ID, so it's only valid in one session. And then the EVSE, so the charging station responds with its ID and the session ID. Okay, what's next? We have to discover the service. The car is requesting the charging stations. What kind of services do you offer? Like, do you support plug and charge? Do you support, let's say, was it EMI, so electrical identification memes, so payment cards? Are you AC or DC? So this is step 7 of the protocol, and now we're starting to realize maybe it's DC. And other services like, oh, do the charging station supply me with internet connectivity or anything else? And so this is really far down the road. And if you're unlucky, if you want to do AC with ISO 15118, especially older cars, will just crash by this moment because they assumed way earlier you will go DC, because it's not on their radar yet that you can do this high-level communication also with AC. So also here, with older cars or with non-well-engineered cars, you can run really into issues where you have to disconnect the car from the battery for an hour if you do something wrong here in the protocols. So it's a lot of fun. You can literally brick cars. So authorization of the session. Whatever the car then selects, its preferred meme, so charging station in the previous step provided what methods are available, and here the car then selects if it want to do plug and charge or if it want to go with the classical approach. And what you often see is if the same car connects it again and again, the first time he tries plug and charge. If he connects the same time minutes later, then he assumes like, probably plug and charge hasn't worked last time, so this time I'm not going to try it. This time I'm ignoring plug and charge and I go directly to classical card payment. So all these protocols can behave from one plugging to the second plugging different, because the cars have some logic to rescue the user, but it can really confuse the engineers. And then the car just waits until authorization is granted or denied. And there's probably some timeout to this again. Then the EV is finding out the capabilities about the charging station. So min-max voltage, the typical current, the amount of energy needed, the EVSE responds with its capabilities, again, what kind of voltage ranges it supports. Then also it could be schedules exchanged, like what is your preferred pricing time frame, so which time do you have what energy available to which price. So they will exchange that capabilities at both times, both directions. And then we slowly go towards delivering power. First, charging station switches to state C. So on this PWM signal, it signals that between plus 6 and minus 12 volts. And the battery is still disconnected. And that means the EVSE closes its output connector and supplies 500 volt temporarily. And then the car is not really connected to the battery, and then everything is measured with the maximum voltage available. If there's any short circuit in the cables, if there's maybe moisture entered, if someone cut it to the cable. So this is just a safety check. And then this waits until the charging station says like, yeah, everything is good. Oh no, there's a fault, I have to stop the session. Yeah, and by the way, in the industry, there's currently some initiatives going on for a new protocol version to do a lot of the steps which I just showed you in parallel. So yes, there will be new protocol versions which will change this once again. So we're not at the end of the story yet. But then upside of that new protocol versions is it will be way faster because things will be done parallel. So then pre-charge happens. We check the cable, we checked authorization. Now we have to apply voltage and make sure that the car tells us the voltage of its current battery. The charging station tries to get to the same voltage without the battery of the car connected. So all the voltages level out. You can think about it if you are on a riverboat and you have this different water levels. Before you open a door, you have to make sure the water level on the door is the same on both sides. Otherwise, you would get a lot of water rushing in. With voltages, it's the same. So you try to get the voltages on the connector on the same voltage on both sides. And then if that everything is fine and the car agrees, doors are open, batteries connected. But sometimes cars just do it immediately. They shouldn't, but they do. And this is another way how you can break a charging station. From the electrical side, you have to design for that cars should not always behave as they should. And this is really safety critical with all the currents. Actually, there's you can have sparks here which welding metal together. So it could be that if you're just connecting, that you'll never be able to disconnect again. So better be able to plan for that. Next, current demand. Actually, battery connects controlled by the EV. In a loop, you're requesting your target voltage, your target current. The EVSE just provides that, and the EV can always exit this loop. The charging station can ask for stopping supply current, but actually the charging station is not in command here. Yes, it provides the currents and the voltages, but the car is in control. And as soon as the power is shutting down, the charging station is also opening up relays and goes to state B. And then we're detecting if any of these connectors after charging welded accidentally together. I mentioned there's huge amount of currents rushing in and rushing out. So it could be that weldings happened. So the EV and the EVSE try to measure that if everything is still fine for the next session. Otherwise, you should go into permanent failure. Then the session is stopped. High-level communication is turned down. Then the CP, PWM signal is switched to permanent 12 volt. And from this moment, you actually could recover and start charging again. But what we saw in the market, almost no one implemented that, because if you do supercharging on the highway, why should you pause and then continue charging an hour later? Normally, if it's done, the car is full, you are disconnect and then you drive away. But actually, there are use cases in the truck industry. If you're connecting your truck at Friday evening to the charging station, maybe it charges overnight, isn't moved at the weekend. Monday morning, the truck is preconditioning, it's cooling, heating, whatever of the battery, and then you start driving. But if you do this preconditioning from your battery, that means you're not starting with 100% on a Monday morning, which is stupid. You're still connected to the wire. So you should be able to restart a charging station. And yeah, we got asked by some big car, I think it was Volvo, they asked around on many of this plug fest, like, oh, can you help us with implementing this? They ask everyone in the industry because they really, really need that for their trucks. So if you build charging station, make sure to build that in. And then there's two different ways of recovering, depending on how much you turned down the sessions. Anyway, end of the day, you're unplugging your vehicle, and then the session is stopped finally. Okay, let's go to hardware. What's there? A rough block diagram of a charging station. So you have typically on the bottom the power pass. You're starting with 400 volts, 3-phase AC, and you're ending with plus minus DC. So how do you do that? You first transforming AC to DC with this huge racks of typically the 5 or 10 very common Chinese power supply makers. Yuya Green, Tonya, InfiPower, Huawei, you name them. You can put them in parallel. So you can have many of them. One unit typically supplies you with 20 to 40 kilowatt, maybe even 60. If you need more, you put them in parallel. Then you have your DC power meter, typically with Eichrecht, isolation monitor, I mentioned that before, and then you have contactors. And yes, this is a bit more simplified because actually, if you do a really industrial grade charging station, you also have to do a special bypass for pre-charging. So in the initial charging phase, you're not connecting directly to DC, but you're connecting via a resistor. So if the car accidentally connects you directly to the battery and your voltage isn't right, that you not have a couple of 100 amperes flowing, initially you're just connecting through a big resistor, let the voltages level out, and then you're removing the resistor from the wire, and then you actually start charging. So here it's only simplified. So what else is on the chart? You have one computer controlling all of that. He's connected with CAN bus to the AC/DC power meters, typically with CAN bus on Modbus or Ethernet to the power meter, to the isolation monitor, and then some GPIOs to the contactors. And yes, he also drives with a PLC modem for the CP communication, and he has a second circuit typically for the PWM signal generation. So basically this upper part is all I talked about before, all the sessions. But this is only the modem. The protocols itself are running on this controller. You can buy them from a couple of vendors. This controller is also connecting to the internet, OCPP protocol. He connects to a human interface, displays, RFID reader, payment terminals. So he is in control of all of that. Typically, you don't want to build all of that yourself on the controller. So we have a couple of partners we do that typically with. So on the right side, you see all the big silicon makers. Texas Instruments, NXP, Analog Device, Renesas. And I think there's a third or fourth one coming. We're also working with Lumicil. They all build reference designs on how to build a charger controller. So they want to sell you chips. So they're really happy to explain you how to build such a computer. So they have free designs available with their dedicated silicon. And in order to get that charger controller running, they need software. And that's what we do. I show you later. But we also work with a different set of charging controller makers, so you can give you the ready-made PCB. And we also have, come there to a second. We also have our own hardware. We'll show you in a minute. It's open hardware. It's just, again, as the silicon makers, you can get all the schematics, all the GABA files. You can just copy that as an inspiration for how to build a charging station. So we do everything open source at Pionix. So all the software on this main head of the charging station, or on this controller, is free available. That means you can just download from the internet. There's no license issues for you. You can use that source code, modify it, change it, sell it commercially. The only thing you can't do is suing anyone if something doesn't work at plan. And it's created by, I think, more than 50 corporates currently. So it's many companies who collaborate on getting that software where it should be. Typical system requirements. It runs on a Linux system, single core ARM processor, 1 gigabyte RAM. We typically recommend 4 gigabyte of flash. You should have Ethernet, Wi-Fi, maybe a 5G modem if you need that in your application. You should have CAN bus or RS485 for connecting all the peripherals. You need this PLC modem. So far we work with Lumicil, Qualcomm, Vertexcom. We will also work with anyone else. But in principle it also works with way weaker systems. So 128 megabytes flash and RAM is enough for EVerest. But really depends on how you configure it. So this is how we build our example charging station, taking a 19-inch rack, put it on a piece of wood, put some wheels underneath, and then wiring that up. And all the designs you will see here you can get freely from the internet, so you can copy that and take your inspiration. We're using a Raspberry Pi microcontroller for the CPPP signaling. We're using a Raspberry Pi Linux system for the high-level communication. We're using Raspberry Pi for the low-level and power pass. You can also build an AC charger with it. Everything is here in the internet. Yeah, and the full diagram, again, there's something missing here for the pre-charge resistors. And then you can build a really, really nice DC charger at the end with all included. So I guess this video, will it work? Probably not. So coming to the software side, how you actually build that. Let me try. So this is an example how to build an AC charging station. I show that video because it gives you an idea. The software is made really, really modular as a charging station. The charging station you saw, we had a block diagram of different blocks. Also for the software side, you can click the blocks together in the same way. So for example, a central state machine, an energy management, a driver for a certain CPPP signaling board. Whatever board you need, there might be a driver already in that, or you build your driver yourself. The ISO communication, and so on and so on. You can configure every module. For example, for the ISO and OCP communication, we have different modes. We have one mode we're calling standard compliant, the other one mode we're calling real world compliant. For example, a lot of cars have timing constraints which are, let's say, non-compliant to the standard. So if you would stick to the standard 100% as a charging station, you couldn't charge a single Tesla. We see that issue a lot in the field. So you have to willingly be more relaxed on the requirements in order to make it work. There have been a famous story from, I think, Daimler recently had a big issue with a firmware update, and I think they broke most of the superchargers out there. And I think Alpitronic and some others then had to fix it. So built in a workaround in their charging station to make the bug of Daimler to disappear. It's not the way how it should be, but this is how our industry works. The charging station maker, you're the weakest component here, you're the fastest moving component. You have to fix the issues from the others. And this is how it would look like afterwards when you build a DC charger. You have again your power pass with drivers for the AC/DC components, with drivers for the DC power meter, isolation monitor, CPPP signaling circuit. You have Slack communication, ISO communication, RFID reader, authentication manager, OCPP module, system module for software updates and timing and whatever, human interface connectivity to displays, energy management paths for load balancing, and a state machine in the middle managing all of that. But you can easily also build, I have no screenshot from this, we deployed that software from, let's say, small home wall boxes to supercharger parks, where one central machine manages more than 100 satellites in DC, with one central OCPP client running all of that. So as hardware can be modular and flexible, also software can be. And our mission here with EVerest is we want to build software building blocks for this entire industry. So whatever you do and whatever comes next, we'll have you covered. Not on our own, but with many, many companies doing the software together. So this is our take on the industry of different standards evolving over time, from grid connectivity, cloud, AC, DC. In the bottom you see the Asian standards, you see the European standards. So everything what's green here, it's done. Everything what's blue is work in progress. And if you would zoom in, for example, on OCPP, there's so many sub-components you can or you can't do. I think the requirements list on 2.01 is like 1,000 or 2,000 line items of things you can or can't do. And our goal here is to get everything in, and that's why we're working with many players in the industry. Tech overview, it runs on, I mentioned a lot of the protocols we're doing. It runs on every programming language. You can write modules from C++, Rust, Python, JavaScript. We have these building blocks. You can integrate it easily in rapid prototyping systems like Node-RED. We have automatic testing, in our CI/CD, we have Docker containers. You can deploy a virtual charging station, including a simulated car in a Docker container. So also great if you're a CPO and you want to test against a lot of charging stations. This is easy for deployment. It runs literally on all the CPUs. We have deployed it on every Linux system out there. Typically Yocto, that's what almost everyone is using. Yeah, and as I said, you can do a lot of different configurations from AC/DC, hybrid, energy management. You can distribute it over several machines in the future, organizing different parts of the software stack. And yeah, and we're not only doing the software for the charging station, we're also deploying this now, this idea of this software for the charging industry on a bigger scope. Pionix and my company started that journey 3 years ago on the firmware side. We have a sibling project from S44, Citrino S. They're deploying the creating the OCP cloud side stack. And we're also wondering if we even do a open hardware reference design project with a couple of companies soon. If you're interested to just use that, or to contribute a bug report, or to ask a question, just reach out to all the EVerest folks here on the table, or to me. We're really, really happy to get you here. And if you need any commercial support, so this is a small advertisement block. If you don't want to do it alone, come to Pionix. We're happy to help you on building your next amazing charger. Thank you. And now, any questions? And I also brought backup in case I'm not able to answer everything here.
Any questions? Anyone dares ask a question?
Otherwise, I will start asking questions. Who's doing hardware here from the audience? Or hardware-related things? 5-ish. Anyone already tried EVerest? Already played with it? 1, 2, 3. Half of the hardware. Almost all the hardware guys. Cool. Oh, there's a question.
Hi, I'm Andy from Huawei. How fast can I build a charging station or a prototype of a charging station?
Can you come a bit closer?
Sorry. How fast can I build a prototype of a charging station with the system?
So the cube I showed you some slides ago, I think assembling that takes us 2 days or so. And I mean, the components are all off the shelf. Probably most time will take you to buy everything. Like you have to buy some Chinese power supply there, then some power meter somewhere else. So I think just chopping the components is the most effort here. Then plugging it together is maybe 1 or 2 days, and getting the software straight. Yeah, if you have a controller where the software is pre-installed, then it's easy. And then you can start playing with it and building on top and making it your own product and making it even more amazing. Because what we want to build is the boring stuff. That's what we want to cover here. And you should do the interesting stuff on top.
Test.
Hello. I have a question, and the question is: are you also developing on EV side a stack, and how far is it along? Maybe.
Okay. Yeah. So we have EV side stack to a certain extent already. The problem with EV side stacks is if you want to deploy it in a car, you need automotive certification. That's not what we want to do. So this is too much overhead for us for the processes. But we're anyway doing EV side stack for simulation purposes. So we have Dash 2, we have DeanSpec already running, based on Joseph from Switch EV, now Ecog. So we utilize that for the time being. In parallel, we're replacing that with C++ code, which will be ready, I think, in 1 or 2 months. Our goal is to have, for productive deployment, no Python in the loop, because it turns out no one likes Python in a in-field environment. It's good for prototyping, it's amazing, but an in-field embedded system, people don't like it. And we will also have the Dash 20 on this EV simulation ready in, I think, 4 weeks, 8 weeks, depending on which feature you're asking. And yeah, we're also deploying that in our own EV simulator boxes we use for hardware in the loop testing. And in theory, we haven't brought it this year, but we have our own small kids electric vehicle which can drive around, which can charge at the Tesla charging station, and it just runs our EV simulator code. Yeah, it's not certifiable from Automotive Spice, but it doesn't matter for these purposes. Anyone else?
Any
Okay.
other questions?
Then, thanks you for your attention. If you have any questions in private, just come over. We're here all day and tomorrow. And have a great show next days.